lesson, we're going to be learning about quadratic functions specifically. So a couple of objectives here. We're going to first talk about graphing quadratic functions using something called standard form. And another thing we're going to talk about is maximum and minimum values of a quadratic function. I think the second topic is extremely important, but can really only be done by learning the first topic. Quadratic functions are really the start of us learning about something called a polynomial function. So let's first talk about a polynomial function. So in discussing a polynomial function, it's defined by a polynomial expression. A polynomial function of degree n can be written in the form here: a sub n, x to the n, a sub n minus 1, x to the n minus 1, plus possibly a bunch of other terms all the way down to a sub 1, x to the first, and then a sub 0. Now, what does that mean? Essentially, what we mean here is these a values here, these are just going to be constants, okay? And we call them the coefficients. And then we have x to different powers, starting with whatever the highest power is. Typically, we write it that way. It's not necessarily needed, but we write x to the highest power, and then the power starts dropping slowly until we get to an x to the first. And then the last term, which doesn't have an x in it, is called the constant term only, and that would be your polynomial function. And so we've talked about a couple of polynomial functions already when we talked about linear functions, in that if we have p of x just equals to a sub 0 just being a constant, there's no x in this function, that's called a constant function, and that would be a linear function, specifically a horizontal line. And then we have p of x equals a sub 1x plus a sub 0, in which case x is just to the first power, and that would be our linear function, very similar to if we wrote mx plus b, just replacing a1 with m and a sub 0 with b. It doesn't really matter what you call them. These things are standing for constants. That would be your standard linear function, which we've already talked about. So what we want to do is talk about a quadratic function. And in a quadratic function, we're dealing with the p of x equals a sub 2x squared plus a sub 1x plus a sub 0, in which case we're basically dealing with a second power polynomial function. Again, this, and this all being constants. You may be familiar with seeing this as specifically ax squared plus bx plus c. Rather than calling a sub 2, a sub 1, a sub 0, you called it a, b, c, but basically that's your quadratic function. You should be familiar with quadratics in that you have solved quadratic equations, you have factored quadratic polynomials, you have worked with the quadratic formula, you have worked with completing the square, you have worked with factoring as it relates to quadratics. We're going to specifically talk about graphing quadratic functions and what we need to talk about in terms of maximums and minimums. Like I said, a quadratic function is really just a polynomial function with the highest power being 2. So we talk about the degree being 2, and so we look at this ax squared plus bx plus c. Typically, we don't want a to be 0, because if a was 0, there would be no quadratic or squared term, and then therefore we'd only have the linear portion of it, and it wouldn't be a quadratic. It would be a linear. So this is the type of function we want to deal with. So first, to start talking about graphing a quadratic function, we'll talk about the simplest quadratic function, in that the simplest quadratic function would be when a is 1, b and c are both 0. So we have a 1 here, but b and c are 0. If that's 0, this whole part goes off. So we are purely just looking at 1x squared. And in looking at 1x squared, or just x squared, this function, we could determine what the graph of that simplest quadratic function looks like, and we would see that the graph of a quadratic function is what we call a parabola. It has this basic U shape to it. We could easily get to this point by just making an xy chart, okay, or f of x chart, however you want to think about it. And we place some x's in, so let's say -2, -1, 0, 1, 2. Figure out what f of those values are. We would get 4, 1, 0, 1, 4. We could then plot those points on an f of x axis, and you would see we would get points that look like this. And we would have this shape here, which is this U-shaped graph, okay? I didn't do it very much justice there, but it would have this U shape to it. We call that shape a parabola. We'll have two different looking parabolas, one where we have this upward shaped parabola, another one where we have this downward shaped parabola. We'll get into that, but largely it has to do with the value of A. If A is positive, we'll get the upward. If A is negative, we'll get the downward shaped parabola. But again, we'll get into that a little bit more later. Ultimately, though, this is the shape of every one of these quadratic parabola functions where they are functions of x. Again, that's the simplest one, but we're going to want to deal with more of this complex one where we do have a value of b and a value of c, and maybe a is not even 1 anymore. Either way, the shape should always fall into one of these two categories, this parabola or this parabola, when we're drawing it. Now, where it's located in the xy plane will change, but the shape generally will either be an upward U or a downward shaped U, or again, we call that a parabola. In my opinion, the best way to work with the graph of a quadratic function is to talk about it in what we call standard form. Okay? Standard form is to convert your long form quadratic, your ax squared plus bx plus c quadratic function, into this form here where we talk about this as standard form. Now the a here is the same a here. However, you notice there's no b or c in this standard form. We now have an h and a k. To get from the form that you're used to the standard form, we use something called completing the square, which you should have some background in. We'll review that in a second. But once you have a quadratic in standard form, you could easily draw the graph of the function. And you would do it using two basic things. And we can use more if we really want to get more detailed. But with these two basic things, you can get a very decent graph in terms of doing largely a lot of things that you're looking to do. One is to talk about the vertex. And if you have it in this form, whatever h and k are, that would be the values of your vertex. Your vertex is a point. That point will either be the minimum point, in this case it's the minimum or the lowest point on your graph, or it will be a maximum point. In this case that would be your maximum point on your graph. But that vertex is that pinnacle point, top or bottom, of the u that is your parabola. So that's a very important point. Again, hk, h coming from what's being subtracted from the x inside this square, and k being the value added after that fact. Those values would be the values you would use to pick out your vertex. Another thing that's extremely important is to determine whether the parabola opens up or opens down. Again, like I said on the last slide, A is going to determine that. If A is positive, greater than 0, you have the upward. If A is negative or less than 0, you have the downward. Those two things, the vertex and whether you open up or down, really are quite a bit of information and can simply be found by looking at a standard form quadratic function. Okay? The trick is, how do we get to that standard form? Okay, so you should be familiar with completing the square. However, we'll review it here. It really is based off of a simple algebraic formula, ultimately. And the idea is, if you had a expression u plus v squared, this is called a binomial squared. The multiplied out version of that would be u squared plus 2uv plus v squared. That's if you did u plus v times another u plus v. And if it was u minus v, the only real difference is this would be a minus here in front of the 2uv. Other than that, everything's the same. So it's based off of this general concept. Now, the idea here is, if we just had this much of this polynomial, and we could then figure out how to add this last part onto it, then that means this entire polynomial can be factored this way. This is the way I think of completing the square. And so the idea is, well, we would have to figure out what v is so that we could add it onto the end here. Well, how do you do that? You do that simply by saying, all right, well, there's a v right there. So if I could figure out what that v is from the piece that I would have, and again, I'm saying I would have this much, and I'm trying to create this part. I got to identify the v from right here. Well, in order to do that, probably the easiest way to do it would be to eliminate the u, eliminate the 2, and whatever's left is the v. So how do I go ahead and do that? Well, I do that in 2 steps. So let's say this is 2 again. First, I identify the u. Well, how? I figure out whatever's being squared here, that's my u. And if I do that, I'm going to pull that out of here and get rid of it. All right, so the only thing left would be 2 times v. Well, if I have a 2 times v and then I divide that by 2, only thing left would be the v. And once I identify that, I can add it squared there. Seems a little complicated, I'm sure, but let's look at something real quick. So let's say I gave you x squared plus 8x. And again, I'm saying that is this part right here, u squared plus 2uv. So the thing that's being squared right here, that's my u. In this case, that's this, which would make then the 8 the 2v component. So if that's 2v, if I simply divide by 2, I would get 4. That would be then my v term. That's v. v is equal to 4. Well, if v is equal to 4, if I add 4 squared, you probably can't see that very well. If I add 4 squared onto the end of this polynomial, that's basically adding the v squared. What does that allow me to do? It allows me to factor this entire polynomial as u plus v squared. What was u? X, the thing that's being squared here. What was v? 4, the thing that's being squared here. So x plus 4 squared is how I would factor that polynomial. Not quite sure that's right. Well, let's try another one. How about x squared plus 12x? Again, remove the u. In this case, the u is the x. So that means this is the 2v. Divide that by 2. What do I get? I'm going to get 6. So if I then add 6 squared onto the end of this, again, that was just this divided by 2, goes there. Add that squared onto the end of it. That allows this polynomial now to be factored as x plus 6 squared. And everyone goes, well, what happened to the 2? Well, x plus 6 times x plus 6, which is x plus 6 squared, is x squared plus 6x plus 6x plus 36. Well, that would be x squared plus 12x plus 36, 36 being 6 squared, and I would get exactly this. So that seems easy enough. Yes, but it can get a little more complicated. Also, what if this was x squared minus 12x? Well, it really wouldn't change a whole lot. X squared minus 12x, I'd still add the 6 squared, but then I would have x minus 6 as my factor. I would still take this divided by 2 and get 6. I'd still add that squared onto the end. Because there's a minus here, there would have to be a minus here. So that's the only thing that would change. But there could be other complications as well. Okay, so the first complication that can occur is what if this x term isn't an even number? So dividing by 2 gets a little trickier. So x squared plus 7x. It's the same setup though. X squared plus 7x, okay? What would happen? X squared plus 7x, we would get, divide this by 2, 7 halves. And I would have to square that. And you're saying to yourself, oh, square 7 halves, okay, that's not bad. But you don't actually have to square it. You know by adding this square onto the end that whatever this is, it's factorable as x plus 7 halves squared. X because that's what's being squared here, the 7 halves because that's what's being squared here. And so the fact that this isn't divisible by 2 doesn't really make it that much harder. You just have to take whatever it is, divide it by 2, and add it squared onto the end. In which case, all right, there you go. X plus 7 halves squared. Again, if it was a minus here, there would just be a minus here, but still not that much more difficult. All right, so that one's not too bad. If this isn't divisible by 2 as easily as the other examples I gave you, it's still pretty much the same process. The next one makes things a little bit harder, but still the same general idea. So what if I don't have a 1 in front of the x squared? Every example I gave you had that 1. Well, that's the key. You need to have that 1. So if I gave you 3x squared plus 12x, okay, and I said, all right, let's complete the square with that. Well, the first thing you want to do is factor that 3 out. So x squared plus 6, let me factor correctly. X squared plus 4x, okay, would be left. And then what you're going to do is you're going to have to look at this now with a 1 in front of the square. And the second that happens, now we're back to where we were. Take this, divide it by 2, and add it squared onto the end here. In which case, 4 divided by 2 is 2. Add it squared, you get 2 squared, and you're good to go. So we would have 3 times, now this thing inside would be x plus 2 squared, and we would then have our square from this. If you had something like 3x squared minus 15x, that would still be okay. Again, you want to get a 1 in front of the square. That would be your first thing. We would factor the 3 out. We'd have x squared minus 5x. Oh no, that's not really divisible by 2 easily, but doesn't matter. What I'll do is I'll just add whatever that is divided by 2 squared onto the end here, and that still is going to allow this to be factored as x, in this case because that's a minus 5 halves squared. The 3 should still be outside, and there is our factor. Okay? Okay, one more thing now we need. The last piece we need is we're going to have a quadratic that looks a little more than this or this. When we're working with it, we're going to have a constant on the end here. So some c is going to be on the end here. Well, we only want to focus on this part and this part. It doesn't matter that we don't have a c there. We will look at what happens with that c and how this whole thing develops in one more step. Okay, so if we had, let's say, 3x squared plus 12x plus, 7. That was our quadratic expression. And we wanted to put this in standard form with completing the square. Okay, let's put everything we learned together. We're going to focus on just the x's. We're going to ignore this 7 for a little bit. Just leave it there. So what we're going to do first is we want to write this as a square. We need a 1 in front of the x squared. It isn't. So first we'll factor the 3. That'll give us x squared plus 4x. Okay? Again, we still have that plus 7. Then we're going to take this 4 and divide it by 2. That'll give us 2. We're then going to square it. If we squared that 2, okay, that will allow this to be written as x plus 2 squared. Now, here's the thing. We just added something to this expression. And I was doing it all along, but in ignoring the fact that we can't really just do that, right? So the idea here is, what did we just add? We just added 2 squared, but not just 2 squared, because that's inside these parentheses with this 3 on the outside. So technically we added 3 times 2 squared. So 3 times 4, 12. So we have an extra 12 that we didn't have before. So what we have to do is cancel that out. So I'll still have the 3 here. I still have the 7. And since now I have an extra 12 that I didn't have before, I'll have to then subtract that 12. You know, if I add it and then subtract it, it's basically as if it wasn't there in the first place. They cancel each other out. So if I subtract the 12 here, then what do I have? I have 3 times x plus 2 squared, and this would then be minus, what would that be? 5. Okay? Now notice, what do we have now? This expression is in the a times x minus h squared plus k form. This is now in that standard form. Okay? In which case h would be -2 and k would be -5. Why did I say h was -2? Because it's x minus h In this case, I could write plus 2 as negative 2, in which case negative 2 is being subtracted, and I always have to look at what's being subtracted, and therefore it would be negative 2. I don't do that here because it's plus k, so whatever this is, that's my k. Easiest way, if you want, opposite sign of here, same side as here, that's your hk, that's your vertex. A the whole time was 3, and that is my A. Okay? So now let's work with this.
All right, so here's the problem we're going to do. We have a quadratic function. We're going to try and express this quadratic function in standard form. From there, we're going to find the vertex, the x and y intercepts. We'll sketch the graph, and then we'll talk about the domain and range of the function. Okay, so in this function, the coefficient for x squared is not a 1. We talked about when it comes to completing the square, you need to make sure that leading coefficient is a 1. So we're going to have to make it a 1. So what do we have? So we have this f of x equals 2x squared minus 12x plus 23. Okay, so there were two setup pieces to our completing the square. One, this leading coefficient had to be a 1, and 2, we didn't really need this constant, and we would move it to the other side of the equation. Now, we're not solving a quadratic equation, okay? So we're actually not going to go through all the steps of completing the square. So what we're going to do is we're just going to say, well, let's just move this constant down a little bit so we could ignore it, and let's focus on the x's. So let's look at the setup again. We want to get a 1 in front of this x squared. Now, there's a couple of ways we can do that, but when it comes to working with functions as opposed to equations, what we're going to do is we're going to factor that 2 out, giving us x squared minus 6x. I'll leave a little space, and then I have this 23 just sitting over here. Okay, so now when we look at this piece right here, that looks like what we would work with when it came to completing the square. So we would take this term right here, we would divide it by 2 and square it. So if we did that, we would get negative 3 squared. And that would allow us to take this thing here and write it as a square. And so we would have x minus 3 squared. Now this 2 is still out front there. Okay, so that's still going to stay there. But also, we can't just add this in, right? We have this idea that when it was equations, if we added something to one side of the equation, we have to add it to the other side. Well, when it comes to functions, we're basically working on one side of the equal sign. So rather than add it to one side, add it to the other side, if we add something to one side, if we also subtract it, that'll cancel it out just as well. So like, if I have something like I add 7 and subtract 7 to some function, okay, well, this cancels itself out, so it's really like I didn't do anything to the original function in the first place, right? So here I added this negative 3 squared. Well, negative 3 squared is 9, but that's also inside these parentheses. So the idea is that this is actually 9 times 2, okay? So what I have here that I didn't have in the original function is an extra 9 times 2, which is 18. So I actually added an extra 18 to this entire function. So if I subtract 18 from this function, that will cancel itself out. So this in here factors as x minus 3 squared. That 2 is still there. And then I have 23 minus 18. 23 minus 18 is going to give me, what, 5. Okay? And so now if you look at that, that is a function that's in that form a times x minus h squared plus k. And we would say, oh, well, we're going to move it this way, left and right, and this way, up and down. So minus 3, move it to the right 3 units, plus 5, move it up 5 units. And then the 2 since it's positive, we're not going to flip this quadratic over at all, but what it'll do is it'll just stretch it vertically. And we said before, that's not going to make a huge difference overall in how we graph it. All right, so from our standard form, like I said, we're going to move 3 to the right and 5 up. So if we go 3 to the right and then 5 up, okay, we're at this point 3, 5 as our vertex for this parabola. So there's our vertex. Our y-intercept can easily be found by letting x equal 0, so essentially finding f of 0. Plug 0 into the function here and here, we would get 23 as an answer. Now, x-intercepts are found by letting y equal 0. Well, f of x is our y, so f of x equals 0. So we set the function equal to 0 and solve. Then we can find our x-intercepts. Well, it's as simple as taking this quadratic function and setting it equal 0. Well, that's a quadratic equation, which we know how to solve. We could use the quadratic formula. So when using the quadratic formula, what you see here is that you plug your a, b, and c in, simplify the quadratic formula, you end up with this. But here's a problem. We got a negative inside the square root. So when we're dealing with real numbers, we would say that x has no solution. And if x is supposed to be solution, okay? If x is supposed to be the x-intercept, then we have no x-intercepts, okay? So put that all together, and we can get our graph. So our function 2x squared minus 12x plus 6, we could also say is 2 times x minus 3 squared plus 5. Okay. So we could see we could take a quadratic, a squaring function. We'll go right 3 units. We're going to stretch by factor 2, and we're going to go up 5 units. Okay. So if we were to graph that, we would go right 3, 1, 2, 3, okay, and up 5, 1, 2, 3, 4, 5. Okay. We're going to be an upward parabola here. All right. And so we have this 3, 5. Okay. All right. If you notice, there's no x-intercepts. Okay. A y-intercept would be 23, which would be all the way up here at 23. Okay. So, see, everything that we found essentially would be verified with this graph. Now, the last thing we want to do is talk about domain and range. Well, it's a polynomial function. For polynomial functions, the domain is going to be all real numbers. Why? Because I can plug any x I want in here. Okay. So my domain is going to be the interval from negative infinity to positive infinity. Okay. Now, what about my range? My range are my y values. So in this case, my range are going to be all the y values I have on the graph. Well, in this case, this is the lowest point. This is the minimum point, okay, on the graph. And that minimum point has a y value of 5, okay? Now, every point after that, since this is going up from there, is going to have a y value bigger than 5. So as far as the range goes, my range is going to be from 5 to infinity, okay? It's going to be everything 5 and bigger. So I'm actually going to include 5 in that range as well, because that is a y value I have. So let's look more at maximum and minimum values here. This is not difficult to do, considering we know how to do standard form now with completing the square. So like we said before, if we have an upward shaped parabola like this, okay, we would say our vertex would be our minimum point, okay? It would be the lowest point in the graph. If we have an upside down parabola like this, our vertex would be our maximum point. So A is positive, we have a minimum, and that minimum would be at hk, our vertex. So we plug h into the function, we would get k, okay? And if a is less than 0, so negative, we would have a maximum value because it would be an upside down parabola. And if we plugged h into the function, we would get k as an answer. Okay, so essentially k would be the maximum y value. Here k would be the minimum y value. So when we're trying to find the minimum and maximum values of the function, we're basically looking for the minimum maximum outputs for the function, and therefore looking at the minimum maximum y values. But this can all be done as long as we have standard form. It's actually really easy to figure out what that value would be. Okay? So here is another quadratic function. All right? It's not in standard form. So what we're going to want to do is we're going to want to put it in standard form so that we can easily graph it using our translations, and therefore easily find the vertex and the minimum or maximum value. Okay? This should say minimum slash maximum value because we don't know what it's going to be. It depends on whether we have an upward or downward parabola. Now, right away, you can look at this and go, oh, I know I'm going to have an upward parabola. Okay? Just because that number out in front of the x squared is positive. So if it's an upward parabola, I know I'm going to have a minimum. So I can now scratch out max. Okay? So we're going to do all these things for this function. Okay, so first thing I want to do is setup. Setup, I want this leading coefficient here in front of the x squared to be a 1. So the best thing I'm going to do is I'm going to look at the x terms only, not the 49. Kick the 49 down. Ignore the 49 for a second. Just look at the x terms. I'm going to factor 5 out of those x terms. Give me 5 times x minus 6. Okay? Then I'm going to look at that x minus 6, and I'm going to complete the square with that. Again, ignoring the 49. Just look at this. If I take this term right here and I divide it by 2, I'll get 3 and square it. Okay? So that's where that 9 comes from. Now, if I look at this in here, I just created a factorable polynomial that is x minus 3 squared. Remember, because this is negative 3 squared. But I can't just add this in here. It wasn't there before. So in order to cancel it out, what do I have? I have an extra 9, but not just an extra 9. I have an extra 5 times 9. So if I subtract an extra 5 times 9, that'll balance it out. So then what do I have? I have 5 times this. This is factored as x minus 3 squared. And now the 49 comes into play. 49 minus, in this case, 45. 49 minus 45 would give me a 4. So now we have our standard form. Now what's going to happen here? This is going to say I'm going to move to the right 3 units. And this is saying I'm going to go up 4 units. Okay? So if I went right 3 and up 4, I would have my vertex at 3, 4. That would be my minimum value because it's an upward parabola. I could also find the y-intercept and the x-intercepts. Well, you see, there wouldn't be any x-intercepts for this one also. Our y-intercept can be found to be 49. It's going to be all the way up in there, and that's just finding f of 0, and that would give me 49. Other than that, there's not much to this, okay? We have a minimum value of 4, so that when I found f of 3, I would get 4. I plug this as my x, this would be my y, because that's the point I'm working with. The smallest y value I could possibly get, and that's what we're looking for when we say minimum value of the function, minimum output of the function, that would be 4. And everything after that would be higher than 4, okay? All right, so let's look at this next one. F of x equals negative x squared plus x plus 2. So let's put it in standard form, we'll sketch the graph, and then we'll talk about the maximum value. In this case, it will be a maximum value because of the negative. Negative means we're going to have an upside down parabola. Upside down parabola means the vertex would be our max. Okay? All right, so first, standard form. Well, what do we got to do? We got to make this leading coefficient a 1. So it's a negative 1. So I'm going to factor the negative out of the x's. Again, ignore the 2. Just leave that 2 kind of off to the side. We have x squared now minus x if you factor an x out. Then what I need to do is I need to take this coefficient right here, which is a -1, and I need to divide it by 2. So that'll be -1/2, and then I need to square it. Well, -1/2 squared is 1/4. Okay? So 1/4 is what I'm going to add here so that this can be written as a square. What square? X minus 1/2, because that's what's being squared. Okay? Now, what did I really add to this whole thing? -1 times that is what's there now that wasn't there before. So if I have that -1 times that, I have to subtract -1 times that. That's what I added, so that's what I have to subtract, which is basically -1/4. Subtracting a -1/4 is +1/4. So this right here would be 2 plus 1/4, which is 9/4. So I get negative x minus 1/2 squared plus 9/4. So what does that mean? 1/2 to the right, 9/4 up, flip it over because of the negative. So 1/2 to the right would be here, 9/4 up puts me here. My vertex is 1/2 9/4. It's flipped over because of the negative. So the maximum value we would get is 9/4. That's the y value. For the x value in the vertex, that's our maximum value. If you look at that a little bit closer, okay, when I say maximum value, remember, it's the y value for the given x. So if I plug 1/2 into the function, if that's my x, that's the y that would come out. Okay? Input, output. All right? So the maximum y value that you can get, the biggest value you can get from this function here is 9/4. You can plug anything you want into the function, any x value in here, you can plug into the function, but the biggest y value you'll get is 9/4. So just to review, when you express a quadratic in standard form, it's definitely going to help you sketch the graph. It's definitely going to help you find the maximum and minimum values. Okay? And we got to understand that how we complete the square really is based off of understanding the quadratic equation steps for completing the square and using that for this quadratic function, mainly the setup. The a has to come out, and that constant c we just ignore for a while, and then we work with what's in here and create a square out of it. Okay? So now let's look at an application of a quadratic function. So a local newspaper currently has 84,000 subscribers at a quarterly charge of $30. Market research has suggested that if they raised the price to $32, they would lose 5,000 subscribers. Now, assuming that subscriptions are linearly related to the price, that's a pretty key part there. What price should the newspaper charge for a quarterly subscription to maximize their revenue? So, yes, if they raise the price by $2, they'd lose 5,000 subscribers. However, they're still making $2 more per quarter per subscriber. So, yes, they're losing subscribers, but they're also gaining money per subscriber. So that's something we want to talk about in order to maximize their revenue. If they raise the price too much, they'll lose too many subscribers and therefore will start losing money. But if they want to maximize their revenue, we can look at this in terms of a quadratic function. So revenue is the amount of money a company brings in. We should know that. In this case, the revenue can be found by multiplying the charge per subscription times the number of subscribers. So revenue would be C times S, where C is the charge per subscription and S is the number of subscribers. Okay? So since the number of subscribers changes with the price, remember they're going to lose subscribers as they raise the price, we need to find a relationship between those variables. So we know that S, which is 84,000, and C, which is 30, okay? And if they raise the price by 32, they lose 5,000 subscribers. giving me a second pair of values of C of 32 and S of 79,000. So for this, we can find a linear equation relating the two quantities. Treating C as the input and S as the output, the equation will have the form S equals M times C plus B. Linear equation. The slope being the change here in the number of subscribers over the change in the price. Okay? Giving us negative 5,000 over 2, or negative 2,500. This tells us that the paper will lose 2,500 subscribers for each dollar they raise the price. Okay? Now, you could have deduced that by saying, well, 5,000, they raised it by $2. Therefore, if they raise it by $1, they'd lose 2,500. It should all make sense. So we can then solve for a vertical intercept, the y-intercept. So in this case, if we say, all right, well, S equals M times C plus B, M being negative 2,500 times C plus B, all right, then let's find the B. Well, we know when we have 84,000 subscribers, okay, $30 is the cost, plug that in, you would then solve for the remaining variable, B, and you get 159,000. So if we take care of that, we would then get the linear equation S equals negative 2,500C plus 159,000. And this relates the cost and the subscribers. All right. Why we went through all that is because our revenue equation has two variables in it, right? C and S. We really don't want to deal with two variables. We would like to deal with one variable, specifically one variable in a, say, quadratic equation. And so, well, in some ways, if you really want to argue it, we could say we have three variables. Revenue is one, C and S are the other two. And we can't have that many variables. So anyway, the reason why we went through all that stuff is so we can write S in terms of C. So this is what we found S to be. If we plug that in for S, then our revenue is C times all that. Well, if you distribute the C into both of those pieces, you would then get revenue equals negative 2,500C squared plus 159,000 times C. Notice that is a quadratic equation, specifically a quadratic equation where the coefficient in front of the C squared, the variable squared, is negative, giving me a negative parabola. Now what we're trying to do is find the maximum of that negative parabola, therefore maximum of the revenue. Okay, that's what we're looking for. The maximum of this parabola, the parabola representing the revenue. All right, so the revenue will go up. Okay, if you follow this, the revenue will go up to a certain point. As we keep raising the price and raising the price, the revenue will continue to go up, but there's going to be a certain point where you're going to raise the price too much, and then therefore the revenue is going to start coming down because too many people canceled their subscription. So that's going to tell us the exact spot where that happens. All right, so if we were to find our height for this, we would have to find our H and then therefore our K. So if we look at our H, right, what could we do? Well, we could take these values here and we can use our formula to find H if you wanted to do that. In which case, we would take this negative 159,000. That would be the value in front of the linear term. That's what we typically would call our, say, B. Okay? Then we'd have our A, which is here. And so we have to divide by 2 times that. Okay? Do that math and you get 31.8. That's your H. So what's that tell us? Okay? That tells us that that would be the X value typically, or in this case the C value for this. So this model tells us that the maximum revenue would occur when the newspaper charges, C is the charge, $31.80 for a subscription. Okay, $31.80. So when they went to that $32, that went too high. So if we wanted to then figure out what that maximum revenue would be, well, then we just plug that into our revenue equation, which is back to here, because that's the C value ultimately. And then maximum revenue would then be $2,528,100. Now, notice they wanted to raise the revenue to $32, okay? Well, that's past this point, which means then the profit's going to start coming down, the revenue is going to start coming down, and therefore the 32 is too high. $31.80, that should be the sweet spot of where you raised the revenue enough and didn't lose enough subscribers so that you would be able to maximize your revenue. Now, it's a little complicated to do what we're trying to do via algebra. That's ultimately what we're using here. We're using algebra to find a maximum. And when you do it for a quadratic or a parabola, we can make it happen. We can do it. And you saw this process of what we just did. Now, if we had access to calculus, we would be able to expand on this far more than we can here in algebra. This is the most we can get out of what we know in algebra. Quadratics, finding maximums, finding minimums, we can do that. If we had access to calculus, which would be the next step after this class, we would be able to expand on this type of problem and, in my opinion, be able to do it, I think, in a far easier fashion. And we would really be able to talk about maximum profit, maximum revenue, okay, and seeing how a company can really increase their profits as much as possible without losing too many customers. But, we are where we are, and this is the type of problem we can do. And so, you see, this is exactly where we're at. And we can do this problem as long as we stick to a quadratic, which means we have to do fairly simple setup problems, and this would be one of them. So to review some of the things that we just talked about, if we're trying to maximize revenue or profit, these are what we want to do. First, use the data provided to create a demand equation relating price and quantity demanded. This typically will be a linear function, and it kind of has to be right now so that we can do the problems based off of the knowledge we have. Right? Then we want to create a revenue equation. You start with your revenue equation, which is price times quantity. Then we want to substitute that demand equation we found in the original number 1 step so that the revenue equation really only has one variable, and that would be in terms of the quantity. Okay? Then after that, if the problem is to maximize, say, that profit or that revenue, we could look at it in terms of either. If we wanted to do it in terms of profit is going to be revenue minus the cost. But if we just wanted to do revenue, we could do that as well. Next, we want to find the vertex of that revenue or profit function that we're dealing with. Profit is just a little bit more involved than just plain revenue. So find the quantity that would then maximize either that revenue or that profit. And if needed, use that quantity with the demand function to find the price that would maximize that revenue or profit. So sometimes just knowing, okay, what the cost is one thing, but then you want to go in and say, well, what would that profit or revenue be?